Thank you so much. It's been a pleasure to be a part of this so far. The talks have been spectacular. The field is in an amazing place, and it feels like things are accelerating even. So I'm really excited about the direction of the whole field. Okay, so this is a fluids talk, but the techniques come from relativity. And of course, there are interesting open problems that involve gravity, and I'll mention some of those at the end of the talk. Okay, so I'm going to present some works in progress with Leo Abbrescia. They're very long, and we're almost done writing, but we haven't posted the paper yet. We sort of keep discovering new things about the problem, and this is slowing down the writing. Okay, so strictly speaking, the results that we have written concern the non-relativistic 3D compressible Euler equations with vorticity and entropy. So that's important for reasons I'll touch on in a little while. And nonetheless, one can develop a parallel theory for the relativistic Euler equations, say on the Minkowski background. So if you fix the Minkowski metric, and say in R1 plus 3, and so you can sort of like make statements about both systems at the same time, because the same mathematical structures that you need to prove the results are found in both systems. And the focus of today's lecture will be on solutions that start off smooth and end up forming a shock singularity. And for reasons to be explained, I want to extract a huge amount of information about the character of the singularity. And I want to mention that I'm considering what I think is the simplest possible regime to obtain these results, which is a regime of solutions where there's no dispersion. So that means you don't have to worry about powers of t or powers of r. The entire focus of the analysis is about the structure of the singularity. One could also imagine addressing different solution regimes where there's dispersion. So this regime without dispersion can be thought of as perturbations of plane symmetric solutions, but there's no doubt that one could also treat perturbations of spherically symmetric solutions where dispersion becomes important. Moreover, if instead of looking at relativistic Euler on Minkowski backgrounds, if you preferred to look at the fluid equations on your favorite fixed space-time, then I have no doubt that qualitatively all of the results that I'm talking about today would carry over. Okay, so these are basically can be thought of or can be arranged so that they're large data blow-up results. And if you fix the space-time, the space-time itself has nothing to do with the large data blow-up of a fluid, at least for the kinds of data that I'm talking about. Okay, and like I said, the focus of today's talk is mainly perturbations of plane symmetric solutions, where the perturbations do not have to be plane symmetric, and the perturbations are allowed to have vorticity and entropy. Okay, so that's kind of the scope of the talk. And now I'm going to lead with the headline, which is this picture. Okay, so I'm going to spend quite a bit of time on this slide because a huge amount of what I want to say is contained in this picture. So this is the picture that I'm working on with Leo Abbrescia, and it contains a lot of different regions, some of which are part of the scope of our work, and some of which are open problems which are not part of our work. So for convenience in the writing of our paper, we took the perturbations away from plane symmetry to belong to the 2 torus. So that's where the x2, x3 coordinates live on the 2 torus, but that really was just for convenience. There's no reason why we could not have taken the perturbations to live in R2. You know, it's a local problem with finite speed of propagation, and you know, we just tried to pick the simplest possible thing. Okay, so one should think that smooth initial data are given on sigma 0, where this is really a flat slice. You can think that in Minkowski space, you fixed your favorite inertial coordinate system, and this is really just t equals 0 in that coordinate system. And I've given some initial data, which are perturbations of a plane symmetric initial data. And the theorem says that under certain assumptions on the initial data, so open assumptions, I should say, open with respect to some high order Sobolev topology, then the following picture emerges. And let me again stress that this hypersurface called K, this is not something that we have derived. This is an open problem, and I'll say a lot more about that. So here's the picture, at least the part of the picture we've addressed. So we've split the analysis into two works. In the first works, what will happen, or what is happening, is the development of what is called a first singularity. So this is called the pass boundary of B. And this ends up being, in the regime we're treating, a codimension 2 space-like submanifold. In fact, if you take X2, X3 to live on the torus, this will be topologically a 2 torus embedded in 4-dimensional space-time. So this is the pass boundary of a codimension 1 hypersurface called B. So B is the singular boundary, and it is precisely on B in this picture where one sees blow up. Okay, and what is happening is some first derivatives of the fluid are blowing up along B, and everywhere else in this picture, there's say below B and even along C, there's no singularity. Okay, no singularity. The only singularity occurs on B, and there is a sense in which the notion of first singularity is the entire pass boundary of B. Okay, so this is the proper notion of first singularity from several points of view. And the question is, how do you derive this picture? Again, I'm not saying anything about K yet. That's not a problem I'm working on. This is connected to the shock development problem that Igor Radnyansky spoke on the other day. Okay, so the first order of business is, how do you obtain this full surface of blow up with a special focus on the first singularity? Okay, and one of the key difficulties, which for those of you who know the relativity notation, is that this singular boundary B is actually foliated by integral curves of a null vector field called L. Okay, so there's a sense in which the singular boundary is null because it's foliated by null integral curves, if you want. Okay, so that sort of tells you, for those of you who have derived PDE estimates along null hypersurfaces, you know that certain degeneracies pop up when you're trying to do estimates on such surfaces. And of course, we run into those difficulties in this problem with the added difficulty that things are blowing up along this entire surface in a very specific way. Okay, in the second paper that we're writing, there pops out of this first singularity a Cauchy horizon. Okay, a Cauchy horizon, and as it turns out, nothing blows up along the Cauchy horizon, except down here at the first singularity, which is a common submanifold, both of the Cauchy horizon and also the singular boundary. Okay, one of the key difficulties that one has to grapple with is that this first singularity, especially in the regime we're considering, but more generally, this first singularity does not have to have any convexity properties. This is just some codimension 2 submanifold in space-time. And if you're perturbing a plane symmetric solution, that means you're perturbing a flat torus. So in this picture, you should think this is just some tiny Sobolev perturbation of the flat line. Okay, and even though tiny neighborhoods may exhibit some kind of some kinds of convexity, the picture or the first singularity as a whole does not have any good convexity properties. And so that poses some serious difficulties. The serious difficulty is tied to the fact that you cannot hope, due to lack of convexity, you cannot really hope to see the full structure of even the first singularity if the only thing you're using are flat, if the only kinds of space-like foliations you're using are by Cartesian flat hypersurfaces. So if you want to see the structure of this first singularity, say by doing PDE estimates on hypersurfaces, there's no way you can touch this entire first singularity by using flat hypersurfaces. So in other words, you're going to need better foliations of space-time to see these structures. Okay, so why do I care about this picture? So one thing that pops out of this work is you get a localized statement about the structure of the maximal development of the initial data. Okay, and so this is a space-time local statement at the moment. One can maybe try to hope to globalize this across space in certain regimes, but that's not a problem. That's not a result that's part of our papers. Really, we're just looking at a local region of space-time. And the statement is that locally, the boundary of the maximal development is this Cauchy horizon together with this singular boundary. Okay, and so of course that's a nice statement to have mathematically. You understand a portion of the boundary of the maximal development. Another key reason to be interested in this picture is because, as we heard from Igor the other day, ultimately you may want to try to understand weak solutions. Okay, and weak solutions are in the region below the first singularity. They agree with the classical solution. But as soon as you have a first singularity and you impose the proper notion, the proper weak formulation of the flow, the weak and classical solutions will actually disagree. Okay, and the region where they disagree is precisely the region trapped in between this hypersurface K, which is something that one would construct if you're studying the weak solution. So K will actually be the hypersurface of discontinuity. Okay, if you manage to solve that problem, the problem is open in full generality. The problem of constructing a weak solution in the neighborhood of the first singularity, it's open in full generality, but it has been solved in under certain simplifying assumptions, which I'll describe later in the talk. And the point I want to emphasize from the point of view of this picture is that the correct notion of initial data for the so-called shock development problem of constructing the weak solution is to have the state of the solution on the Cauchy hypersurface all the way down to the singular boundary. And then it's quite helpful. It's not totally clear that it's essential. It's quite helpful to have, for purposes of an iterative construction, it's quite helpful to know the solution all the way up to the singular boundary B, even though part of this region will ultimately be discarded, in specifically the region in between K and B. The classical solution in that region will be discarded and replaced with the weak solution once you actually construct the weak solution. So the singular boundary and the information up to it actually serve or can serve as a mathematical barrier that helps you construct the shock hypersurface when you actually go to solve the shock development problem. And something that's interesting is that the shock hypersurface K actually starts off tangent to the singular boundary. So in some sense, there's initially there's no room here, and if you really think you're trying to construct the shock hypersurface, you kind of know you're going to need a lot of information, at least in the vicinity of the first singularity. Okay, so parts of this picture have been obtained under various assumptions. So parts of this picture were first obtained by Christodoulou in the irrotational case, but even in his breakthrough monograph in 2007, where he was treating irrotational solutions, he was only using Cartesian flat foliations. So he does not get the full picture of the first singularity in regions where you don't have convexity. And moreover, this is I want to again emphasize that we allow for solutions with vorticity and entropy. And one of the key difficulties that I'll come to later, which connects back to this picture, is that the way we know how to approach the problem, there may be other ways. I'm sort of neutral about that, but the way that we know how to approach the problem relies on elliptic estimates for the vorticity and the entropy. And we have to have a framework that allows one to derive those elliptic estimates all the way up to these surfaces B and C, which again are not, they have nothing to do with the Cartesian flat foliations if you want. Okay, so we need a framework that can allow us to do these elliptic estimates, and as well as the wave estimates and all the other estimates on basically arbitrary surfaces. Okay, so here's just another picture of why this surface called B is the singular boundary. What you see represented in this picture is the piling up of the characteristics along the singular boundary. So these, I haven't really mentioned what the characteristics are yet. I'll turn to that later in the talk. But here you can see in the picture, there are 3 characteristics, and they're initially separated a bit, and then they bunch up here. And it turns out that they don't actually intersect on the singular boundaries. There's some kind of degeneracy. It kind of reminds you of the degeneracy u goes to u cubed near the origin, u equals 0, but the precise details of the degeneracy, the way these characteristics bunch up, is directionally dependent if you want. So I'm going to avoid those technical details. And one thing that may not be apparent from my picture, which maybe it's not a perfect picture, but all of these hypersurfaces, these characteristic hypersurfaces PU, they're actually tangent to the singular boundary. You know, they so that sort of shows you another degeneracy. Each of these characteristics is tangent to the singular boundary in exactly one codimension 2 submanifold. Okay. And as it turns out, and it's well known in many contexts, the bunching up of these characteristics is tied to the formation of a singularity and the first derivative of one of the fluid variables. Okay, so that's sort of like the motivating pictures behind the talk. And now I just want to spend the rest of the talk fleshing out as many of these ideas as I can. Okay, so maybe I'll make some more asides on what happens after the shock. Okay, so this is the shock development problem. So starting from a first singularity, initial data, let's say on a Cauchy horizon, and let's say that you know the classical solution below the singular boundary. You may try to construct the weak solution in a neighborhood of the first singularity. And so this was done around 2016 by Christodoulou-Lisebach in spherical symmetry in 3D. So they did it for relativistic Euler equations. And I'm going to stress a point that Igor mentioned the other day in his talk, which is that there's a difference between understanding the transition of the solution from smooth to having a first singularity to having the initial weak solution. That's shock development, understanding that transition. There's a difference between that and putting the initial data, putting the shock into the initial data, which is what Maida did in his famous works from the 80s. So there is definitely a big difference between seeing the transition and from smooth to weak, and actually putting the shock into the data and then studying the evolution of the shock. So this paper is really, and the whole shock development problem, that's really about the study of the transition. Okay, then in his breakthrough 2019 monograph, Christodoulou looked at the n-dimensional relativistic and non-relativistic Euler equations with no vorticity or entropy, and he, if you want, proved short time local existence for a weak solution. And as it was pointed out in Igor's talk, that's called the restricted shock development problem. And it actually amounts to solving a divergence form system, PDE system in weak form, that doesn't exactly coincide with the Euler equations, precisely because there's no vorticity or entropy. And the full problem of understanding how to construct that local weak solution past the first singularity when you have vorticity and entropy, that remains open. I believe Christodoulou may be working on that. That's but in any case, it's a great open problem. There was a recent result by Buckmaster, Driebusch, Scholar, and Wickel, where they looked at 2D compressible Euler, and they looked in azimuthal symmetry. So this is a symmetry class where basically you can do transport equation estimates. You don't have to do L2 space estimates. And they allowed for vorticity. So this is the first result where for a solution to shock development problem where you have some vorticity. And they produced they gave a full proof of sort of existence and uniqueness within the class of solutions that satisfy the estimates, unique existence and uniqueness of a local shock development. Okay. And so I mentioned this result earlier, this result of MIDA. If you put initial data, if you take initial data that have shocks, then MIDA produced in his works the local and time weak solution with vorticity and entropy. And then we heard the fantastic work of Dan and Igor, where they went to the restricted shock development problem in a regime where there is near spherical symmetry, and they constructed a global and time solution. Okay, so this is the first global and time unique weak solution to the restricted shock development problem. And so I personally think this is a great breakthrough. Okay, so but that was just more of an aside, sort of reasons to maybe give you to care about singularities. Today's talk is not about what happens after the shock. Today's talk is what happens up to the shock. Okay, so let me start giving some ideas on the PDE analysis. I'm going to keep things extremely non-technical because the actual work is very technical, and I don't think there's much value in going into those details. Okay, so there are 3 coordinate systems that we have to work with. First is the standard Cartesian coordinates, or if you're in the relativistic case, Minkowski inertial coordinates, T, x1, x2, x3. And one thing that's very different from Einstein equations is that there's a fixed differential structure that's privileged that you have to care about. So basically, there's a sense, okay, it's very clear for the non-relativistic theory. The theory lives in Cartesian space-time. But let's say if you're studying the fluid on the Minkowski space background, you kind of are forced to think that the fluid lives in Minkowski space, and that the correct real physical differential structure is the one corresponding to the standard coordinates in Minkowski space. So that's very different from Einstein equations. And so as it was noted in the paper of Eperon, Real, and Sibersky, when you have a hyperbolic PDE problem where there's a rigid differential structure that you are forced to work with, you can have non-uniqueness of maximal developments of the initial data. You can have non-uniqueness, and so that's an issue that you actually have to worry about in principle with Euler, compressible Euler, and relativistic Euler as well. The question of non-uniqueness. And let me already back up a few slides and mention that for these particular developments of the data, the classical part of the solution lives on one side of the boundary. So in other words, you don't have like some classical solution below C bar and also above C bar. If you did have a classical solution that somehow touched the boundary of the maximal development from both sides, then that is a warning that there may be non-uniqueness of maximal developments. And so that was first noticed in that paper I just mentioned by Eperon, Real, and Sibersky for a different equation. So for something that's essentially a string equation that can be thought of as a formulation of the Born-Infeld equation. Okay, and if there's time, I'm going to return to this issue at the end of the talk, because you can actually produce, in fluid mechanics, you can produce non-unique developments of the initial data. You can actually do it in 1 + 1 dimensions using essentially Berger's equation. Okay, but we'll see if we have time for that. Okay, so there's the standard Cartesian coordinates. Then there is the iconal function, which is properly called acoustic iconal function in the context of fluids, which you may be familiar with from relativity. So this is a solution to the iconal equation where the metric G is the acoustical metric, which is determined by the fluid. So the correct intrinsic geometry of the fluid is solution dependent, and it has nothing to do with the ambient space-time metric. I shouldn't say has nothing to do with. There are some causal relationships, but in any case, the correct metric is not the space-time metric, it's the acoustical metric. Okay, and the final family of coordinates that I'll talk about are what we call rough adapted coordinates. And you take the x2, x3 coordinates, the flat ones, you take the iconal function, but then instead of the Cartesian t or the inertial t coordinate, you introduce a new time coordinate. In fact, there's a one parameter family of time coordinates parameterized by kappa, belonging to some small interval 0 kappa naught, where kappa naught depends on the initial data. And these are the time functions that are precisely adapted to the shape of the singular boundary. Okay, and something I'll talk about in more detail later is that the singular boundary B, where the fluid blows up, ends up being a particular portion of a level set of a function called mu, where mu has different names in different contexts. In some places, it's called the null lapse. In some cases, it's called the inverse foliation density. It's basically the reciprocal of a first derivative of the iconal function. And the vanishing of mu essentially signifies the formation of a fluid singularity, but really it's a very particular portion of this level set that is part of the maximal development. There's a portion of this that is definitely not part of the maximal development, and I hope to have time to say more about that later. Okay. Now, what about this family of time functions, tau? So each kappa indexed time function tau solves a transport equation. So don't really want to get into the details of what this transport W is, but the transport equation has geometric initial data. In fact, the initial data for the time function are it's the minus sign in front of mu, so the opposite of the inverse foliation density. But it's not given. The initial data are given on a rough geometric hypersurface. So the surface on which the initial data for the time function tau, the surface on which the initial data are placed is one of the unknowns in the problem. Okay, and it ends up being a level set of a transversal derivative of mu. Okay, and this vector field W is adapted to the flow, and it's just much easier to show you pictures of what's going on, and I'm going to do that in a couple of slides. Okay, so what is the strategy? So you take your singular boundary, which at least the portion that you would like to access, and you write it as a union, these T0 minus kappas. And the notation is from the paper, it doesn't really matter. All you need to know for purposes of this talk is that each of these is a topological 2 torus that is provably 2 degrees less differentiable than the fluid. So I'll show you in the picture exactly what's going on. That's coming in the next slide. So you foliate the singular boundary by a family of 2 tori, 1 torus for each kappa. For each of these tori, each of these kappa, we construct a time function, tau kappa. These are the tau kappas from the previous slide, such that the 0 level set of tau kappa intersects the singular boundary precisely in that torus. Okay, so each of these time functions, you can think that I have, a family of time functions. I'm going to do estimates. I'm going to Grandwall with respect to the level sets of tau. And as soon as tau hits 0, I touch the singular boundary precisely in a 2 torus. Okay, and then to get the entire singular boundary, I need to vary these 2 tori, and that's the same as varying these foliations. And consistent with what I said before, the union of these 2 tori, in other words, the singular boundary, is a portion of the level set mu equals 0. And you may ask, so this is for kappa positive. What about kappa negative? So it turns out that the portion of mu equals 0 corresponding to negative kappa is cut off by the Cauchy horizon. Okay, so just there are multiple reasons why you don't have access to the other portion of mu equals 0. One reason is that it's cut off by the Cauchy horizon. Another reason, which is much more technical to address, is that if you think of this portion that's discarded in a limiting sense, it ends up being time-like. And you do not have any PDE estimates available along such surfaces. So you can't even do estimates up to that surface. Okay, but let me not get into those technical details at the moment. Instead, I want to go to the pictures. Okay, so here, are the pictures corresponding to two values of kappa. So let me start with the first picture because this is the most important part of this construction is certainly the first singularity. Okay, so here you have initial data given on sigma 0, some smooth initial data, perturbations of a plane symmetric initial data. And then what happens in the first part of the evolution is not that interesting. This can be understood from Cauchy stability. You don't need a fancy coordinate system. You can just say, for large amounts of time, the solution stays close to a plane symmetric solution. And then as one gets close to the singularity, certain structures start to become visible in the flow. And it's not until close to the singularity that you can start to construct these other foliations. Okay. So again, this is the case kappa equals 0. And down here, we have, let's just call this like the first available hypersurface corresponding to kappa equals 0. Okay, so the solution induces initial data on this rough hypersurface up here. That's what I'll call it, a rough hypersurface. And then you switch to this gauge corresponding to kappa equals 0, and you follow the solution all the way up until this time function vanishes. So that this time function corresponding to kappa equals 0 is negative down here by construction, and then as it increases towards 0, finally you touch a portion of the singular boundary. And these time functions are constructed so you touch the singular boundary precisely in its past boundary called d minus b, which happens to coincide with t00. Okay, so the point is the PDE analysis is set up in such a way so that you can do estimates all the way up until the very first time where you touch the singular boundary. And these time functions are cooked up so that they exactly intersect the singular boundary in an entire torus. Okay, and then here's what the situation looks like for a positive value of kappa. So this is a different torus along the singular boundary. You have a different initial rough hypersurface induced by the solution corresponding to the same smooth data on sigma 0, but it is a different surface. And then you start doing your estimates with respect to the kappa foliation, and you follow the solution all the way up until you touch the singular boundary, and you touch it once again, you touch it in a 2 torus, precisely in a 2 torus. And as you can see from the picture, the highest member of the kappa family, when it touches the singular boundary, it bends away from it. And it bends away from it on the left, and it bends away from it on the right. And so the bending, the precise way that this bends is achieved by sort of making a good guess about the behavior of the inverse foliation density and using that guess. So it's basically a bootstrap argument if you want, using that guess to construct the vector field W in the transport equation that the rough time function satisfies. So basically, you can make a good guess about how to flow these hypersurfaces in such a way so that they flow away from the singular boundary at the point of first touching. Okay, so the thing you have to do to make this picture precise, of course, is to derive PDE estimates for the fluid on all of these regions. Okay, and again, like no convexity is needed in the first singularity in order for this argument to work. There are some other technical assumptions that are needed to make this work. You can't do this for you can explicitly write down solutions where the character of the first singularity is in fact dramatically different. So for example, you can construct solutions where what you would like to call the first singularity doesn't even have the structure of a manifold. So you need some assumptions in order to have this picture. But I'm not going to talk about those technical assumptions right now. Okay, so let me just mention some key precursor results. There are lots of results, too many to go through in detail. Many people have seen some of the boundary, some of the singular boundary for various hyperbolic PDEs. There's a lot of big influences in the field. So Fritz John in his work in the 1980s was studying singularity formation for strictly hyperbolic PDEs and 1+1 dimensional symmetry. And some of the core geometric ideas about studying the density of the characteristics can already be found in his early papers. Alinak was interested in that picture for quasi-linear wave equations that fail to satisfy the null condition. And he had a Nash-Moser-based framework for following the solution up to the first singular point when there's a unique lowest blow-up point. So I'm going to return to this issue of lowest blow-up point in the next slide. And then the real breakthrough was in Christodoulou's 2007 monograph on irrotational shock formation for the relativistic Euler equations. And his arguments accessed what I would think of as an implicitly defined portion of the maximal development. And I say implicit because he's using these Cartesian flat time functions. And at the end of the day, the biggest statement that's made is that you take the union of all of these developments as you allow the Cartesian flat foliations to tilt while still remaining space-like. And then you can also allow the initial data of the iconal function to vary. You take the union of all these developments and you get something. And that's the conclusion, the big conclusion of the book. And so what we're doing with Leo is actually giving an explicit construction in a single coordinate system. There's only, what I mean by that actually is there's only a single fixed iconal function. And we're doing it in a way that that allows you to access regions of first singularities where you don't have the convexity. Okay. Following Christodoulou, there was a lot of work on wave equations that in principle gave access to the same implicit portion of the maximal development. With Jonathan, we have had a result in 2 dimensions with vorticity, and later in 3D with entropy. And like all of these works, starting with Christodoulou, even if they don't tell you the full structure of the maximal development, they certainly give you the full structure of the singular set at the time of first blow up. So time of first blow up in all of these works means something like Cartesian time. So all of the space-like slices are flat in the Cartesian structure. And there's another approach which is philosophically very different, perhaps a bit more robust in the sense that one can hope to apply it to other equations where geometric optics may not be so easy to implement. So based on modulation theory and self-similarity, they proved a blow-up result when there's a unique lowest blow-up point for solutions with vorticity and entropy. Okay, and I also want to mention, this really important work by Merrill, Raphael, Rodniansky, and Sheftel on implosion singularities, where so implosion singularities are where the density blows up. So this is much worse than a shock. Much worse in the sense that it's not clear how to continue the solution. But they are seeing a portion of the maximal development in the sense that they're seeing finite time blow up. Okay, so here's a different regime, or let's say easier regime. So this is a regime where you have what I will call a strictly convex singular boundary. And so these are the regimes that were basically treated by Alinak and Buckmaster and company. So in this picture, I don't know if you can tell from the way I created it, but there's supposed to be clearly a unique lowest point. So there's supposed to be, if you imagine that space-time is foliated by flat sigma t's, there's supposed to be a unique lowest point in this picture. And that is the point that Allignac and Buckmaster were able to access, was the lowest point in this picture, the lowest singular point. Now, if you do have this kind of strict convexity, then I think it's likely that the arguments that Christodoulou gave for trying to access this picture using Cartesian flat foliations, I think that if you allow yourself to vary those foliations, I think you can touch this entire picture and therefore have access to it. But two things. First of all, you know, for perturbations of plane symmetry, you certainly don't have this strict convexity, even if you have it in tiny neighborhoods. The other point is that if you really want to understand the full global structure of the maximal development across all space, you know, unless you're looking at certain monotonic profiles, you're going to have regions where you don't have this kind of convexity. And so, you know, one wants techniques that don't rely on convexity and that are actually adapted to the object that you're trying to construct. Okay, so much for strict convexity. Let me talk a little bit. I see that I don't have a whole lot of time left. What is the stopping time for this talk?
Yeah, so we started late, so you still have about 20 minutes.
Okay, so I have about 20 minutes. Okay, so the first thing one needs to obtain those pictures is a good formulation of the equations. And there are zillions of ways to write the relativistic Euler equations. You can write it in divergence form as a quasi-linear hyperbolic PDE system, or non-divergence form. In the irrotational case, you can introduce a fluid potential, which is what Igor was doing in his talk. So this D is the space-time D, not the connection of the acoustical metric. So if you're in Minkowski space, this capital D is just the ordinary partial derivatives if you're in the standard inertial coordinate system. And then there's this formulation of Euler as a wave-div curl transport system that in the relativistic case I obtained with Disconzi, that came on the heels of a similar formulation that I found with Jonathan Luke in the non-relativistic setting. And of course, all of these works were motivated by Christodoulou's geometric framework in the irrotational case. And finally, if there's time at the end of the talk, I will talk about what happens in 1+1 dimensions, where you can use Riemann invariance. Because you can gain, even though the full problem is very complicated, you can gain a lot of intuition for what's going on already from the 1+1 dimensional case. So, all right, so then you need to choose state space variables if you want to study the flow. And there are a lot of ways you can do this. Every way that you set up the equations involves the Four velocity. But once you've picked the Four velocity, you're sort of free to choose from among other state space variables to set up the equations. So you can work with energy density, pressure, number density. The variable entropy is you need to introduce entropy if you want to understand thermodynamic effects in the flow. And then you need to assume an equation of state to connect some of these variables together. Otherwise, you don't have enough equations to close the system. So the existence of an equation of state, that's an assumption. But then in addition to the assumption that an equation of state exists, there are other relationships that come from the laws of thermodynamics. And there are other variables that one can define coming from thermodynamics. So at the end of the day, there's a lot of freedom in choosing what your state space variables are. And then all of these equations sort of tell you how to determine all the other variables. But no matter how you do it, certainly a fundamental quantity that comes up in the problem is the speed of sound. You write the pressure as a function of density and entropy. you take the partial derivative of p with respect to rho, you take the square root, that's the speed of sound. And we are only working, the results, that picture that I presented is only applies in the case where the speed of sound is positive and no bigger than 1, which is the speed of light. Okay, so we prefer, for purposes of deriving that picture, to choose the unknowns to be little h, the forward velocity, and the entropy s, where little h is the log of the enthalpy. So big H is the enthalpy. We chose to divide out by a normalizing constant called h bar so that this is dimensionless. These details are not really important. What you really need to know is that you can formulate relativistic Euler flow in terms of the log of the enthalpy, the forward velocity, and the entropy, and you get a first order system that looks like this. It's quasi-linear hyperbolic. And so this is like the starting point for studying the flow. However, this particular formulation of the equations does not seem to have the particular structures that we need in order to derive that picture. Okay, so I'm going to talk about another formulation in a minute. Okay, so I want to talk a little bit about the ideas behind the PDE analysis. Now that I've shown you the pictures of the singularity and the foliations that we're using, I'll talk a little bit about the PDE analysis. So one thing you can do to sort of motivate everything is to go to isentropic case. So you set entropy to be constant. Let's take it to be 0 for simplicity. And one can construct the Riemann invariance. If you also assume, in addition to isentropic, you assume plane symmetry. So it becomes a 1 + 1 dimensional problem. And you can write down the Riemann invariance, and you can write down explicitly the two characteristic directions, these two null vector fields L and L bar. They can be determined explicitly as functions of the Riemann invariance. And then the entirety of relativistic Euler flow reduces to the study of these two coupled quasi-linear transport equations. They're coupled through the coefficients of L and L bar. Okay, so this is one way to think about 1 + 1 dimensional relativistic Euler. And why do I tell you this? Well, you can do something funny. You can take these equations. So these are the same equations from the previous slide. And you can take an L bar derivative of the first equation and an L derivative of the second equation to get second order equations. Okay, and you might say, why do I want to do this? Well, certainly for people who work in relativity, you recognize this right away. This is a wave equation, right? And to study the flow away from symmetry, it is very advantageous to treat the system from a wave equation point of view. Okay, so even though I've taken one derivative of this of the system to get a wave equation, so you might say that's a little weird. Nonetheless, once you have a wave equation, there are many tools that one can exploit. And certainly this is what I was doing with Leo, going back to my work with Jonathan and going back further to Christodoulou, is exploiting all of these tools from geometric wave equations. Okay, so about those waves. So they are wave equations corresponding to the acoustical metric. And in Igor's talk, he showed us what the acoustical metric looks like in the non-relativistic case. And here's what it looks like in the relativistic case, where again, eta is the Minkowski metric. And the important thing for you to take away is that the important geometry in the flow has nothing to do with eta. It's really about the acoustical metric. So when I'm talking about geometric wave equations, it's really the geometry corresponds to G and not to eta. An important computation, which is very simple but very telling, is that the forward velocity, which is originally it's normalized so that it's length 1 with respect to the Minkowski metric. It's also length 1 with respect to the acoustical metric. So it's time-like in length 1. And that means in particular that it's transversal to any null hypersurface, or any hypersurface that's null as measured by G. So, so that's important for doing estimates, because part of this, part of the PDE analysis is to do estimates on null hypersurfaces. And there are transport phenomena in the flow. Okay, you can't necessarily see that from the way, I guess you can see it from the entropy equation. But there are transport phenomena in the flow, and you need to get estimates for the transport variables along null hypersurfaces, and you can do that because the transport operator is transversal to those hypersurfaces. Okay, so it's a really basic fact, but it's also really important. Okay, so here is a very crude statement of the formulation of the equations that Leo and I used to study the flow. This is actually only a statement of part of the equations. This is what we would call the wave part. And this is what I derived with Marcello Disconzi, based on earlier ideas coming from my work with Jonathan Luke. Take your favorite smooth relativistic Euler solution in 3 space dimensions. And for any variable psi, that is one of what I call the wave variables. That's really just any of the unknowns. If you compute box psi, you get basically 3 kinds of terms on the right-hand side. First kind of term is null forms, and null with respect to the acoustical metric. So it turns out that these are, and it's well understood that these are harmless error terms near shock singularities. So these are like good terms that don't screw up the evolution near shocks. And then there's something that's like a forecroll of a vorticity and a divergence of a gradient of the entropy variable. The actual details are rather complicated, so here's schematically the kind of wave equation satisfied by each of these psi's. And the spirit of the analysis is to show that everything on the right-hand side is perturbative. So you want to sort of fantasize that everything is 0. Okay. Now, in reality, the precise nonlinear structure of these terms matters. The theory of shock waves is extremely unstable under perturbations of the equations. If you add your favorite derivative cubic term, it's going to mess up everything in general, because near a singularity, derivative cubic terms can dominate. And why do I say that? Because you can't see it from the way it's written, but all of the terms that drive the formation of the shock wave are actually present on the left-hand side of the equation, hiding in the definition of the covariant wave operator. So in other words, if you expand this out, if you expand box psi out in standard coordinates, you will get terms that are like 1 derivative of metric times 1 derivative of psi, but the metric depends on psi. So those are like d psi times d psi terms, and it's exactly those terms that drive the formation of the singularity. So, if you want, the singularity is driven by Riccati type derivative quadratic terms on the left-hand side. And so you can't just add your favorite derivative cubic term to the right-hand side and expect that the theory is stable, because cubic terms can become dominant near the singularity. Okay, so here's an example of what I mean by a G-null form. It's got to look exactly like this. Cannot be the Minkowski metric. It's really got to be the acoustical metric, and they're known to be harmless near shocks. Now, the big technical difficulty, or one of the huge technical difficulties, is that these 2 terms, the forecroll of the vorticity and the divergence of the gradient of the entropy, if they're not treated carefully, they will result in derivative loss. And so you need to do something to treat these terms. And it turns out that these terms satisfy like a div curl transport system, where the error terms in the div curl transport system also have a good null structure. And you can use this to show that there's no derivative loss in the system under this particular formulation. And in particular, if you're interested in the structure of the maximal development, you have to localize these elliptic estimates. They have to be localized and adapted to the precise shape of the singular boundary. And Leo and I did this in a paper in the non-relativistic case. It's actually quite non-trivial to localize these things, because the original equations are given to you in Cartesian coordinates, or if you want, inertial coordinates in the relativistic case. And so you need div curl estimates for systems on that are given in one coordinate system, but you need to adapt them to a sort of arbitrary hypersurfaces whose structure is not known in advance. So it's actually a very technical part of the work. and I'm not going to discuss it more in this talk. Okay, so let me discuss a little bit of the geometry. When you break the symmetry, you can construct this inverse foliation density mu. This is the null lapse, whose vanishing parameterizes part of the singular boundary. And you can show that at time 0, mu is basically 1. This means that at time 0, the characteristics are roughly equally separated. And then you can construct all of your favorite objects that you see in mathematical relativity when you're using iconal functions and null foliations. You can construct a geodesic vector field by taking the gradient of the iconal function, putting a minus sign. You can multiply by the null lapse to get a different null vector field that is normalized with respect to the flat t. And it turns out that this is a useful vector field to work with, and it happens to exactly agree with the one that's given explicitly in terms of Riemann invariance in isentropic plane symmetry. Okay, and since you have an iconal function, you can start constructing other vector fields and vector field frames out of it. So you can construct an entire frame. So there are advantages and disadvantages to working with a true null frame. It's kind of there are some parts of the problem where instead of working with a double null frame, it's just sort of preferable to work with frames where you have one null vector field that's tangent to the characteristics, and then you have other vector fields, all of which are tangent to constant Cartesian time slices. So it just leads to some simplifications in the analysis. And maybe I'll skip the details and just show you the picture. These are the kind of frames that you're working with. Here you see that the characteristics are initially separated, and now they're starting to bunch up. And then I have this this frame, the characteristic direction L, sort of Y, which represents the perturbations away from plane symmetry. And then the most interesting one, the most interesting direction, not surprisingly, is the direction that's transversal to the characteristics. So that's this X direction, which is weighted by a factor of the null lapse. So it's weighted by a factor of the null lapse, and the null lapse is going to 0. So you can see that this vector mu times X is shrinking as you, so this is, you should think that this is a picture in Cartesian space. So this vector mu times X is shrinking as you head towards the singularity, and it's shrinking in a way that exactly compensates for the blow up of the X derivative of the fluid. And this is just another way of saying that it makes sense to work with that frame because it allows you to derive regular estimates with respect to that frame. So if you rescale the transversal direction in such a way that it goes to 0 as the shock forms, then you can get regular estimates relative to that frame. And that's equivalent to saying that you can prove that the solution remains rather smooth in the coordinates t, u, x2, x3. So basically, if you unfold the characteristics by introducing the iconal function as a coordinate, then you can see that the solution wants to remain rather smooth. And so this framework has a long history in 1+1 space dimensions. And in the context of fluid mechanics without dimensions, it was Christodoulou who first sort of understood the problem could be approached like this. Okay. And the reason why I wanted to show you that setup was so I can give a slightly more precise description of the portion of the singular boundary that you can hope to access through these methods. So the portion of the singular boundary that's part of the maximal development in this setup is the portion of the level set where the null lapse vanishes, together with the portion where the weighted X derivative of mu is negative. So by definition, weighted X derivative means you take the transversal direction, transversal to the characteristics, and you multiply by the null lapse. So that's like a renormalized. You can think that this is, in this coordinate system, t, u, x2, x3, this vector field is effectively d du, so the partial derivative with respect to the iconal function with all the other variables fixed. Okay, so the portion where this is negative, this is exactly the portion that belongs to the maximal development. What happens when this quantity is positive so I mentioned this earlier, in a certain limiting degenerate sense, the portion of this of mu equals 0, where this quantity weighted x mu is positive, actually is time-like in a degenerate sense, and you cannot hope to do PDE estimates along that. And then another thing, which it looks like I'm not going to have time to discuss, is that portion of the surface gets cut off by the Cauchy horizon anyway. So if you're trying to understand the structure of the maximal development, I mean, you have to really hit the nail on the head. This is exactly the right thing to construct, and you can't hope to have access to the portion of the surface where x mu is positive. You know, looking at the clock, I can see I only have like a minute or two left, so I am not going to spend any time telling you about non-uniqueness of developments in plane symmetry. And instead, I'm just going to mention some future directions, things that I think are worth considering. So far, nobody knows how to understand this picture in the context of Einstein-Euler equations away from symmetry. So that could be a very hard problem. In any case, it's from a physical perspective, I think it's worth putting a lot of effort into. It's a great problem. We want to understand how shock waves show up in general relativity. If you go to your favorite GRMHD talk by an astrophysicist, you're probably going to see simulations that show the appearance of shock waves in GRMHD simulations. Okay, so you see them on the computer, and mathematically, it's a great question to try to understand through pencil and paper. Are these things real? Are they stable? Do they exist? Can we say anything about them? I already mentioned this several times. The shock development problem for solving locally past the first singularity is open in full generality. Again, I think Christodoulou may be working on that problem. Now about the long time behavior of solutions with shocks, at least in a perturbative regime. So we heard from Igor the other day that in two space dimensions, that may be very hard. There's no global result known in two space dimensions. But one good thing about two space dimensions is, at least for incompressible Euler, in 2D, it's known that solutions are global in time. Okay, so in incompressible Euler, there's only vorticity. And so vorticity is the only thing that can blow up and screw up the evolution. And in 2D, we know that vorticity does not do that. So it's conceivable that one may be able to find some regime in two space dimensions for compressible Euler with shocks, where one can say something interesting about the long time behavior of solutions. Perhaps not all the way to t equals infinity, but it would already be interesting if you could sort of say something beyond the time that the usual scaling arguments would give you. Okay. And finally, if you like these pictures and you like this theory, I challenge you. I think it would be a great problem if you could sort of extend this to other multiple speed systems like elasticity, crystal optics, nonlinear electromagnetism, where the principal part of the equation is much more complicated and has more indices, and the whole theory of geometric optics would need to be redone in a more sophisticated fashion. So you'd have to develop a new geometry. So this is a very hard direction, very, very hard, but nonetheless, I think it's a fascinating direction. Okay, I will stop there. Happy to take any questions.